Hi, today we are going to talk about radian and degree measures of angles. We can define the radian measure of angles in terms of the circular coordinates of points of the unit circle relative to a length u. The unit length u is equal to the radius of a circle. So if you take a look at this diagram, you can see that I have this circle drawn. My unit length is the radius of that circle, and we are going to assign points along that circle based upon the coordinates when that circle rolls over that line. So let's see what's going to happen. So 1 full rotation is going to be 2 pi radians. Now, there's one disadvantage of radian measure. It is extremely useful in upper level mathematics, and it's used almost exclusively in trig eventually. But the radian measure has a serious disadvantage for everyday use. The measures of all common angles are irrational. This is because any fraction of a circular rotation, like 1/3 rotation, a half rotation, 5/6, or even 1 full rotation, is an irrational number because it's based on pi. So to allow commonly occurring angles to be measured as natural numbers, we're going to use a system that dates back to the ancient Babylonians. We call this measure degree measure, and our book calls it U degree. So we call this unit length a U degree, or UDEG for short. 360 units for 1 full rotation of the unit circle between 0, O, the origin, and P is 360. So the circle starts here, we spin it around, and it lands here at 360 degrees. You'll notice that when we're talking about degrees, we are including 0, but going up to and not including 360. And just a little bit of vocabulary, 180, we say, is the U degree coordinate of Z. The U degree circle is coordinatized with values 0 through 360. So we're going to propose a method to measure an angle for when that angle's vertex is on the center of a circle. So we're going to let A, B, and C be non-collinear points in a plane pi. So let's take a look. A, B, and C, non-collinear. They're going to form an angle. Let U be a length, and let C be the circle in pi with U radius 1 and center B. So I have my circle here. I have A, B, and C. My circle has a U radius of 1, and we want to talk about how to measure this angle. There are unique points, P and Q, such that the rays of my angle intersect my circle at these points. So ray BA intersects my circle at point P. Ray BC intersects my circle at point Q. And we're going to say the U degree coordinates of P and Q, we're going to call them little p and little q respectively, where P and Q are somewhere between 0 and 360. We propose to define the U degree measure of the angle ABC, as the absolute value of the difference in the coordinates. And we're going to denote it by M sub U DEG of angle ABC. We would read that the measure of angle ABC in U degrees. Now, there's a problem with this measurement. The problem is that it's ambiguous the way it's defined. And this problem stems from the fact that as you're looking at it, you can't quite tell, based upon where the origin is and what the circular orientation is, if you're talking about this measurement here or this outside one here. So we're going to have to come up with a way where we decide what we're going to call the measure of this angle. But we're going to talk about that, and I'm going to show you a proof of why our definition at this point is ambiguous. So when the origin is placed at a point other than P and Q, the results are different based on the circular orientation of the points with the origin. The issue is that depending on the location of the origin and circular orientation, the resulting measure is either x degrees or 360 minus x degrees. So here's the proof of the problem. What I have drawn over here on the right-hand side, is that is a circle. I have an angle here with vertex at A, and AP is that way, AQ is that way, and we're going to define a couple different coordinate systems along that circle, and we're going to see that the measurements come out differently if we just consider the absolute value of the difference in the coordinates. So to see this, we're going to consider the diagram at the right where the outside we give u degree coordinates relative to point K. So looking here at point K, we're going to make that the origin. And along the outside, I have the coordinates going around 0, P, R, and Q. And on the inside, we give u degree coordinates relative to the point K prime. Here's K prime. Notice in the diagram, KPQ, KPQ has a positive orientation, whereas K prime PQ has a negative orientation. Now, by moving along the circle from K through P to K prime, K through P to K prime, and then on through Q and on to K, we make one complete circuit of the circle. Hence, it seems reasonable to agree that r plus r prime is 360. So let's look at that again. So if I look at my coordinate here, it's 0. And I measure to there. My coordinate is r. Now, from K prime to K, all the way back to K again, is r prime. So if I'm adding these two together, it must be 360 because it's all the way around. Furthermore, since both inner and outer u degree coordinate systems have been constructed to have positive orientation, it follows that Q is greater than R and P prime is greater than R prime. So let's take a look. Q here is greater than R because we're going counterclockwise around, and P prime is greater than R prime because, again, it's going counterclockwise around. By examining the diagram, it is then reasonable to agree that since the two coordinate systems stem from the same length u, Q minus R must be equal to Q prime minus 0, or Q prime. So let's take a look. Here's Q on the outside minus R. That has to be equal to Q prime on the inside minus 0 because it's the same distance here and we're using the same length u. So Q minus R is equal to Q prime, and P prime minus R prime must be equal to P minus 0, or P. Here's P prime minus R prime, that's on the inside. That has to equal the outside, P minus 0, or just P. Then from 3 and 1, we can conclude that P prime is equal to this expression. So where does that come from? Let's take a look. So from 3 and 1, P prime, if I look at this here, P prime would have to equal P plus R prime. All I did was I added R prime to both sides. Now I'm going to look back up at 1 here. looking at this, I can solve this for r prime. R prime has to equal 360 minus r. Therefore, I can now make a substitution. P prime must be P plus 360 minus r, and that takes us to statement 4. Hence, from 2 and 4, now I'm looking at 2 and 4, P prime minus Q prime is equal to this quantity. Well, look at P prime is here minus Q prime here, Q minus R. And then we simplify and we find that P prime minus Q prime is equal to 360 plus P minus Q. So all we're doing is distributing this negative, the R's cancel out, and that's what I end up with on my right-hand side. And if the quantities are equal, the absolute values must be equal as well. Now we can see that we have a problem because if I just subtract P prime minus Q prime, that may be equal to 360 plus P minus Q, like what I said. We can't tell if we're talking about this distance here or this distance on the outside. So now I'd like you to work on exercise 99. I'd like you to try and prove that these two quantities are equal. Press pause on your video, and when you're ready for me to talk through the answer, press play again. So here is my answer. So let's talk it through. We're going to let P and Q be elements of real numbers such that P is greater than or equal to 0, Q is greater than P, and both of those are less than 360. We're going to complete the proof that this absolute value, 360 plus P minus Q, is equal to 360 minus the absolute value of P minus Q. So in each text box, you enter a rational arithmetic expression in the variables P and Q. So let's see what happens. We show that each of the above two expressions has the same value as the other expression that does not involve absolute value signs. Okay, so we are first going to come up with an expression that is 360 minus the absolute value of P minus Q. And then we're going to come up with an expression for this absolute value. And then we're going to see that those two quantities are equal. So let's see what happens. I know that 360 minus the quantity P minus Q is equal to 360 minus Q minus P. And the reason for that is that P is less than Q. So if I know that that's the case, if P is less than Q, this will be a negative number, but then I'll take the positive of it. So if I switch the order here, I will get the same value. So that's equal to 360 minus this quantity. And then distributing the negative, I find that's equal to 360 plus P, the quantity, minus Q by the associative rule. So next, since Q is less than 360 and P is greater than 0, it follows that Q must be less than the sum of 360 and a positive number. Q is less than 360, therefore if I add something to it, it still has to be less than that. Now, I take that and I subtract Q from both sides. So I know that 0 is less than 360 plus P minus Q. And thus, I now know that the absolute value of 360 plus P minus Q is equal to 360 plus P minus Q. So once I've gotten here, I now know that I have the same quantity here as I did here. And therefore, since these two quantities are the same without absolute value, this guy must be equal to that guy. And you can see that's the case here. Now we'd like to come up with an agreement to eliminate the degree measure ambiguity. So let's take a look at what this is. Let A, B, and C be non-collinear points in a plane pi. So again, we're going back to this. We are defining A, B, and C as non-collinear points so we can form an angle with those. And let U be a length, and let C be the circle in pi with U radius 1 and center B. Let P and Q be points such that C intersect BA is P here, and C intersect BC is Q here. Let the U degree coordinates of P and Q be P and Q respectively, where P and Q is somewhere between 0 and 360. Then the U degree measure of angle ABC, denoted M sub U DEG, of angle ABC is the smaller of the absolute value of P minus Q and 360 minus the absolute value of P minus Q. So now we're going to look at this, and we're always going to choose the smaller of the two differences, the absolute value of those differences. So now that we've talked about radian and degree measure, and we've come up with an agreement for how we're going to determine the degree measure of an angle, I would like you to work on exercises 98 and 100. Have a nice day.